Hey everyone, welcome back to our Jetstream AI Basics training. So we're going to be moving on to polynomial regression. If you haven't watched the linear regression video in this series and you're following along, I highly suggest going back to the first video because it'll have some important context. But other than that, let's go ahead and get started. So this time we're going to use a different data set than our previous data set. We're going to use a data set that is about fish. So it looks at the species of fish, their weight, their height, how tall they are along 3 different dimensions. So, how long their fins are, gills are, and whatnot. So that's what we're going to be doing. So the first thing we want to do is read in our data set, right? And then CSV. And then once again, you can copy the file path or get it from GitHub or have it, as I said, once again, copy the file path like I have it currently. So I found my file path and then we will close our parentheses. So let's go ahead and take a look at the first 5 of this data set. Yeah. Dot head. So remember, this gives us the first 5 rows of this data set. So great, you can see all the columns in here. There's species, weight, length, length 2, length 3, height, and width. There's different lengths refer to such things as tail length, gill length, and whatever. You can read more about it in the reference to the data set. So you can see that there, but what we're actually going to do is we're going to drop the species column. We're going to come back to it, but in the meantime, we want to go ahead and get rid of it because we're not going to be looking at it right now. So we're going to use a dot drop, which means you're going to drop a column out of a data frame. And the column that we want to drop is the species column. Spelling does matter. So make sure that you're spelling things right. And axis equals 1. And so what we're doing is we're just dropping that column and we want to make sure all the other columns move over in its place. So, and then we close our parentheses and let's do the head function again to see what our new data set looks like without the species column. So we see that species was dropped, everything shifted. So now we have weight, length 1, length 2, length 3, height, and width of the fish. So why don't we do a little data exploration like we did previously? So previously we did the .describe function, but why don't we use a different type of chart this time? I personally am a more visual learner, so I find that to be super helpful. So we're going to use a box plot to look at the 3 different lengths in this. So we're going to use plt.boxplot. And then we're going to, this is going to be a little bit of a long statement, but we're going to have to call each of the length variables and assign a label to it. So what we're going to do is fish underscore df. And then remember, once again, spelling, capitalization, all that matters, length 1. And then we're going to go ahead and close that. Ooh, wrong type of parentheses. And then we do that again. And we're going to do that for each of the 3 lengths in here. Length 2, fish underscore df, length 3. Right, and then let's go ahead and add a label because we want to be able to know what's what and just make it a little cleaner. So what we're going to do there is labels equal, and then 1, comma 1. Forgot our parentheses to indicate a string length, length 2, and then length. Once again, don't forget your parentheses like I am, or your quotation, length 3. All right. And then we close that out. And then we make sure we close our parentheses as well. We're not done. We want to make sure that this graph looks nice and makes sense. So let's go ahead and add a Y label to it. So the Y label that we're looking at is length. And then why don't we add a title as well? So if you're ever presenting this data or whatnot, it's nice to have really nice graphs that have all the information that someone would need of fish lengths. And then we want to show or print that table. And then there we go. So we see that the different fish lengths, we see their quartiles, right? We see that length 3 is by far the most expansive length, and it also looks like the biggest length. So this could be great to understand, what average is for a fish, what outliers there are. We see that there are some really big fish that aren't to be expected. So I think that's a great way to see things. So let's continue on here. Oops. So we will continue on. Let's look at a different type of chart. We looked at box plots. Let's try to create a scatter plot like we did last time. So fish underscore df dot plot. And let's do it a different way. So kind, you can also define the kind of plot here, and then we'll call it scatter. You can go into the Python guides to see all the different type of plots that you can name from here and what they're called. So we want to let's look at weight related to, I think our weight related to our height. All right, and then let's take a look at that. All right, so you see weight and height it looks like maybe that there's some sort of exponential relationship or something, but we see overall that there's probably a positive trend towards weight and height in the fish. So that's good, just good to know. So we can see that they're likely positively correlated, but we have multiple values here that we're looking at. So what we can do is create something called a correlation matrix, which shows how closely related different variables are to one another. So how we do that is we create a correlation matrix, and that's going to be equal to our data frame fish underscore df, and we're going to call the correlation function to see how correlated they are. And then we want a core matrix. And then what we want to do there, so we actually missed a step here, but what we're going to do is SNS dot, we're going to create a heat map from Seaborn. So what this does is it creates a visual picture of how this will look. We want it to be annotated, which just means we want to be able to see all the values and it have labels and whatnot. You want to make sure you use an equals sign, and then we just want to look at it in terms of decimals rather than percentages. I think that makes most sense, with 1 being perfectly correlated, 0 and negative being, 0 being not correlated at all, negative meaning there's a negative correlation. And then it tells us we have an error because I forgot to close my parentheses. And then once again, spelling matters here. I forgot to capitalize data frame. All right. So once again, Python is a strongly typed language. We want to make sure that we are capitalizing things when they go wrong. So you get small errors like you saw that I just had because I forgot to close my parentheses and capitalize. So make sure you're doing that along the way. So now we have our correlation matrix. So what you see here along the X and Y axes are all the different variables that are in our data set. So we have weight, all of our lengths, our height and width of the fish, and how they're correlated to the other variables in our data set. So the coefficient matrix has a 1. It means that there's a positive correlation between the two items. So when one increases, the other is expected to increase. So when we see length 3 increasing, we expect length 1 to also increase. R of 0 means that there's no correlation. And an R of -1 would mean that there is a perfect negative correlation. So that is how we interpret this correlation map. And it really helps us, especially when we are dealing with bigger data sets that we might have, hundreds of variables, and maybe we want to see which are the best to include in the model if we don't want to include all of them. So that is why we would create this correlation matrix. All right, now that we have done all this amazing exploration, it's finally time to get to our training and test split to prepare for training the model. So what we're going to do is we have our X as usual, fish underscore DF, and then we're going to want to drop just the weight. So that means all of our other variables, we're going to be solving for weight here. We're going to be trying to predict the weight of the fish. So we want a data frame that has everything but. And then Y, we just want fish underscore DF, and then we just want the weight to predict it. All right. And then we do our training and test split like we did in linear regression. So you do X train, X test, Y train, Y test. And then that all equals our train underscore test split. And then we're doing X comma Y. And then we want our test size to be 0.2, 80-20 split being the most common. And we want to set random state as, let's try 53 this time. So remember, random state just saves state, which means that we'll have the same repeatable answers each time. And so we will go ahead and run that. All right. And so as we are running that, next thing that we're going to look at is actually calling our XGBoost regression model. So XGBoost is a type of library in Python. And so what XGBoost stands for is extreme gradient boosting. So it's a machine learning algorithm. It's really known for speed and performance. And it's a decision tree based method. So that means a decision tree is a series of questions leading to different outcomes. So if you think about kind of like flowcharts almost, right? If A or if B, what result do we get? And so that's what it's doing, is it builds these new trees, focusing on correcting the errors of the previous trees and branches. And so this optimizes the process to help give us the best accuracy in this. So what we actually look at in gradient boosting, or what we're going to look at here, is reducing the RMSLE, or the root mean squared logistic error. And so what that means is let me say that again. Root mean squared logarithmic error. And so what that means is we're looking to minimize the differences between the predicted and actual values. And say we have values that are in the thousands, right? And then we have other values that are really small, that are just 1-2 points off of each other. We don't want the algorithm to over focus on the larger values, which is why we use root mean squared logarithmic functions to kind of normalize those values so that the XGBoost model is looking at things equally. And so now what we're finally going to do is we're going to create an instance of our XGBoost model. So we're using XGBoost regression. So you'll put you'll call it something XG underscore reg, and then we're going to call XGB dot XGB regressor, and then we're going to say we want to look at the evaluation metric. So the thing that we're trying to minimize as the RMSLE of the function. And so we have instantiated that. So now we've instantiated our XGBoost regression model, let's go ahead and create a parameter grid. So XGBoost has a series of parameters that we want to attempt to tune to our model, which means we want to see which combinations of parameters give us the highest accuracy for our model. So we use something called a grid search for that. So what we first do is we create a parameter grid. So we'll create param underscore grid, right? And then the first thing that we want to start with is a parameter called max depth. Um, I forgot some parentheses or quotations. So we want to look at max depth and then the values that we want to look at. So max depth is the maximum depth of the tree. So we talked about the decision from the nodes. So how deep do we want to go into the decision-making process? So increasing this value can make the model really, really complex and prone to overfitting. So what we want to do is usually keep it, the range is usually between 1 and 10 is what they use, but we want to keep it in the middle range. So let's try it with 3, 4, 5, and 6. All right, so we close that out. And then we move on to the next parameter, which is n estimators. Okay, make sure you got to use parentheses, quotations on either side of this. So n estimators is the number of boosting rounds or trees to build. So how many times are we going to look into this decision-making process? So more trees can improve the performance, but we want to make sure once again that we're not making it too big where it overfits or too small where it's going to underfit. So it's usually between 100 and 1,000. So let's go ahead and take the middle range numbers again. Let's try 200, 400, 600. I think those three are good for this. And then we move on to our next parameter, which is learning rate. So what does learning rate look at? So learning rate controls the contribution of each tree. So when we make a decision or we run through this decision trees, it'll decide if things are, right, like this is the good way to go, or we need to adjust for our RMSLE. So learning rate will controls the contribution of each tree. Lower values require more trees to kind of come together and like decide on a value, but it can lead to better performance. So we want to keep it, incremental in our changes. And the typical values for this are very small. So we start at 0.01, differences per tree. And then let's also try 0.015. Learning rate is really powerful, so we want to make sure to tune it carefully. Next is booster. So booster is talking about the type of boosting model that we're going to use. We're using XGBoost, but there are different boosters within XGBoost. So there's XGB tree, which is for tree-based models, XGB linear for linear models like we're doing. So this time we want to go ahead and let's try both the XGB linear. So we'll try GB linear as it's called, and then we'll also try GB tree. Tree. So these are different types of boosters. So we can see which one works best for our model here. And then the last thing we're going to do is verbosity. So this is just basically the number of messages you're going to get through the time that a grid search is running. I personally don't like to see a lot of those messages, so I keep verbosity at 0 just so I don't have to see them if they're not needed. And so now that we have our parameter grid set up, we're going to actually do our search now. So we'll create a search and then we'll use this function called grid search CV. CV stands for cross validation. So it'll try to do its best to go through the parameters, figure out which works best, and then fit it to our model. So we're going to call our model. So we're calling our XGReg model that we called in the previous column. And then we want to use our parameter grid as what we're searching on. And then we want it to cross-validate results 5 times. We take all that and then we want to fit that, fit all those parameters that they find best to our X train and our Y train data. And then what we're going to have it do is we're going to have it print the best hyperparameters parameters are best hyperparameters. All right, now that we fit it, let's go ahead and print what are going to be our best hyperparameters. So the best parameters iters are, and then we're gonna have it give us the results from search and like the best parameters from our grid search. And then we close that. Then we go ahead and run. All right, so that ran faster than I thought. But that's one of the magics of being on Jetstream and having great resources. So the best hyperparameters here are we're going to use a GB tree booster, a learning rate of 0.015, max up of 4, and estimators of 200, right? So now what we're going to do is we're going to take these parameters and actually input them into our model before we fit our data on it. So we're going to do XGreg, which is our model, and then we're going to do XGB dot XGB regressor. And then this time we're going to set the parameters. So we're going to say learning rate equals, and then sometimes it's best to just go off of the best params from the search. We don't have to actually type out each one params. You can do it both ways. But in a model that's really big, it might be a lot easier to just put best parameters in case you're adding more parameters to your beginning model or whatnot. And then it makes things a little easier so it can auto update rather than you having to change the values of this model each time. We're going to look at, and we had an estimators, and then that is search dot best params underscore, and then we're going to look here at estimators. All right, and then next comes our max depth. It might have been helpful for me to go in the order it was listed above, but that is okay. And then it is glitching here because I did not put the same parentheses or quotations, params, and then we're going to look at this time max depth. And then last but not least, we have our booster. And in our booster, we'll go ahead and just set it as GB tree, just to give you an example of how you can manually set parameters as well as calling best params. And then as usual, we want to minimize our evaluation metric. Our evaluation metric, which is RMSLE. All right, and then we close those parentheses out. And then let's go ahead and finally fit our model, xg underscore reg dot fit. And then we have x train, and then our y train. And then we will finally, all right, now that we have run our search grid parameters, we have gone ahead and we have added all of those parameters into our instantiated model. There are two ways you can call those parameters that we found. You can either use the best params function and call the learning rate or whatever you were looking at, or you can see what I did in in Booster with GB tree and manually input those parameters as well. And now we're going to go ahead and fit onto that model. And now we can see that this is the equation for our model and it has been fit to our data. So now what we want to do is go ahead and get our predictions. And so what we're going to look at with our predictions is let us predict the y values off of x test. So we're going to do xreg, which is our XGBoost function, and then we're going to do predict, and then we want to predict values from x test. Great. All right, now that we have our predictions from our x test, let's go ahead and look at the root mean squared logarithmic error of the differences between our y test data and our predictions. So we'll create a variable called RMSLE, and then we're going to call the function that looks at mean. We're going to square root because it's root mean squared error, and then we're going to find the mean squared log error of our y-test data and our predictions. Make sure to close your parentheses. And then we're going to go ahead and create a print statement to look at that score. So the score is, and then let's look at it up to 5 decimal places, and then get the root mean squared of our data set. Once again, your spelling matters and go slow because sometimes you get errors like that. All right, so here we see that our root mean squared error is 0.13. There's no exact range of values for root mean squared error. It kind of just depends on the other values that you're looking at. The lower is better, but you should really look at it in terms of the data. So most of our data values are between, we go back to our like box plot, you see a really wide range of data going from 10 to 70. So I would say the root mean squared we have of 0.13 is a pretty good place to be. But like say we want to look at it in terms of a value that's a little more known to us, we can look at it in terms of that R2 score like we did previously in the linear regression section. So we look at the R2 and we get the XG underscore reg dot score, and then we do our, let's look at our x test to our y test data, and then let us print it out. So print out the R2 underscore score, and let's go ahead and multiply that by 100 so that we get a percentage, and then add a percentage to it. So here we see that this formula is 97% accurate. As I said, industry standards are 70 plus. This is a smaller data set, but that means that we're doing a pretty good job of being able to predict a fish's weight based on all of their other things. So let's go ahead and create a scatter plot for this. So we will create our scatter plot as usual, plot.scatter, and then we're going to look at our y test and our predictions, right? And then we'll go here and then we'll create an X label, which is actual weight, and then I didn't finish there, but we can already see some of the values here. So then let's go ahead and create our Y label as well real quick. Y label, which will be our predicted weight. And then we'll go ahead and give it a title. I know we're excited to see the results, but we'll get there. We'll call it XGBoost fish actual versus predicted. And then let's go ahead and create the bar now, create the chart now. So here we can see that there's a pretty straight line, which means the values are adding up pretty well. The few things here that are skewed are okay. But overall, the line is close to diagonal, indicating the predicted weights closely match with the actual weights. The closer these points cluster around the diagonal, the better the model's accuracy is. So we see we have a few little outliers here and there, but overall, we've done a really good job with being able to predict our fish values from a using our XGBoost model. So thank you so much for tuning in today, and then you can go ahead and move on to the next video, which will be XGBoost classification models, where we'll add species back in and work with categorical variables. Thanks, everyone.